Welcome to the fifth and final session on Robotics Camp with MoveIt. Today we are going to look at how to connect the Kinect depth sensor and then use it alongside with planning in MoveIt so that the environment can be dynamically updated. You don't have to include in any collision objects like we did last week. So let's just get started with everything. First thing we're going to do is we're going to look at the simulation we are using already. So I'm going ahead to launch the file, which is the sawyerworld.launch. So we know that this simulation file doesn't have a Kinect sensor included. That's what I just want to show, that then we'll go ahead and then add in the Kinect sensor plugins and then any depictions that we would like to use for it. So whilst my simulation loads over here, we can even go ahead to look at, okay, well, it's loaded, so let's just take a look at it. So as you can see, there is no Kinect sensor on the robot. You can even look at the topics being displayed over here, ROS topic list, and then we'll see that there's nothing related to the Kinect sensor. In fact, let me filter this out. Kinect, and there is nothing. So let's just go straight forward on and then add in a Kinect sensor. Then we can go ahead and then make all the necessary configurations that we have to do to get it running in MoveIt. So first things first, we're going to create a URDF file for the Kinect, and then we'll just include it into the launch file for the robot. What I mean by this is if you go down here to the Sawyer_robot and then Sawyer_description into the URDF file, this is the main URDF that's been launched. That's the Sawyer.urdf.chakro. So we're going to be including the chakro file that we create for the Kinect inside here. So let's just right click here. I'm just creating it in the same folder. You can do it anywhere else, but just make sure the mapping is correct. So new file, I'm going to call this Kinect_sensor.urdf.chakro. So you can now double click to open the file, and then I'm going to copy and paste my description inside here so we can go through step by step. Okay, so now that my file is pasted here, I'm going to switch to the XML syntax highlighting so that everything can be seen clearly. Let me make this window quite bigger, and then we can look at the chakro file for the Kinect sensor. So first thing we're doing here is we have a link that is going to depict the Kinect sensor. For this, you can use any model that you want to use to show the Kinect sensor. There are some already prefabricated models inside the gazebo model folder, but we will not be using those ones today. This one is just a simple cube, a box. Well, it's a rectangle if you look at the whole thing, stretched out on the sides. That's what we're using, and then this is just the material color. This is just basic URDF, and if you're not familiar with URDF, you can go to the Robotics Ignite Academy. We have awesome courses that goes through this. This is just basic creation of a link to depict the Kinect sensor. Next on the menu is the joint. So what we're doing here is we are connecting the Kinect link that we just created, the depiction, what is going to use the representation of the Kinect sensor. So remember, we're calling this link Kinect_link. all right, so what we're doing here is we are creating a fixed joint between the robot's torso and then the Kinect link, and then we want the sensor to be positioned somewhere around this coordinate, is quite above the robot, and I've been experimenting with this and it's quite good. And then the rotation that we want the sensor to be rotated, a little bit tilted. Yeah, that's what we have over here. Okay, so with that done, we create another joint, and this one we're calling the camera optical joint. What are we going to use this joint for? Well, in order to use the gazebo camera plugin, you have to do this, because if you tend to go straight ahead to connect the gazebo plugin, if you want to use a plugin from the Kinect_link frame, you kind of get some weird rotations, and then you have to do a lot of other tedious stuff in order to correct it. But to avoid all this, what you can do here is what you create a link, an empty link. You don't have to put anything in it. So for example, that's what we have here. So I created a link, which is the camera underscore link underscore optical, and then you connect that link using a joint. So the joint name is the camera optical underscore joint. So I'm connecting that link, that empty link that I created, to the Kinect link, to the representation the model representation, but then I'm not transforming it in any way on the XYZ axis, but you have to rotate it using these parameters here. You have to change the roll and then the yaw for the rotations. So you do this, and then your camera, whichever camera that you're using, is going to be orientated and then positioned very well for you. If you don't do this, you're going to have to rotate whatever camera frame that you use for the robot, whatever frame, not camera frame, sorry about that. So what do I mean by this? Here we're going to include a gazebo reference. We're including the sensor plugin to be used, and then we want the plugin to be included using the Kinect link as a reference. So it's going to be attached to the model representation that we created earlier, the Kinect link. And then these are just the variables that we're setting for the camera, the horizontal focal length. Then we have the width, the height, the format for the image that is going to be coming out of it. And then here we're doing the depth camera thing, but you're not going to put anything inside of this tag. Then the far and then the near clipping for the camera. Okay, then here, this is where we actually do the actual plugin startup if you want. So that's we're calling this one the camera underscore controller. Then here is the actual plugin that is going to be attached, which is the lib gazebo underscore ross underscore openai underscore kinect.so. So we setting always on, we setting the update to 10, and then we want the camera name to be Kinect. So whatever the sensor is going to be publishing will be under the namespace Kinect. And then for the frame, this was what I was talking about. If I wasn't using the camera underscore link underscore optical that I just created, which is inside of the Kinect link, it's just a little bit rotated in different ways so that we can have an actual, so that we can have the robot, the images coming from the camera or the depth point or the point cloud, whatever you are using, to be matched correctly. If I wasn't doing that and then I was using any other frame over here, which I was going to be broadcasting statically, using the TF static broadcaster, then you have to do the rotations inside of the broadcast in order to have it to correctly match. But then let's avoid all that tedious work and then do this over here. Once you have this part done, you don't have to do any rotations at all. I'm setting the frame name, that's the frame from which all these topics are going to be published from. I'm setting that to the camera underscore link underscore optical. Then the rest are just basic default configuration parameters for the distortion, the hack baseline. Then yeah, so that's it for the Kinect Sensor.urdf.chakra. That's it for the chakra file over here. I'm going to save, and then I'm going to be including that into the main chakra file, which launches when you use the soya_world.launch. So just right beneath here, we're going to do chakra, then colon include. What are we going to include? Just the same thing. You can copy a line over here and just transform it, just change the line. So I'm going to include the file name, and then what is it? Well, in this case is a Kinect what. First let's find the package, which is a soya_description, and then inside the package, what are we looking? We're looking inside the URDF folder, and inside the URDF folder we want the Kinect _sensor .urdf.chakra. So simple as that. And then yeah, so remember you have to close it you don't do that, you're going to have XML errors and then all that. We don't want that here today. So that's it. You have the Kinect sensor included and then ready to go. Let's visualize it inside Gazebo and then see that everything is up and running before we go ahead and then make the configurations that we need to get MoveIt working with our sensor. So I'm going to relaunch the simulation again, and hopefully, if everything was done right, we're going to see the Kinect sensor positioned inside of MoveIt right above the robot and then tilted a little bit downwards. Okay, so the simulation is downloading. Let's see what we have here. Yeah, right above here is our Kinect sensor. I hope you all can see it. Yeah, so let's look at how the point cloud from the Kinect sensor is being published. Let's see what we have. So I'm going to be using RVS to do that visualization. So rush 1, RVS, and then RVS again. Hit enter. Make sure you bring up the graphical tools window if you are using the ROS Development Studio. So hit login to bring it up, and then what's happening, reconnect. Okay, so far so good. So I'm going to be setting the fixed frame for this here to the base, because that's what we're using. The world will work either way, but then that's the base is actually the fixed frame within which our robot is operating. So that's what we're going to do here. And then for better visualization, let me add in the robot model. Okay, let me close this panel over here. Good. And then I'm going to bring in the point cloud visualization. So let's go down and then select point cloud 2. Double click to add it, and then let's set the topics to, in fact, before we do that, let's look at the topics being broadcasted by being published by the Kinect sensor. So let's do it that again over here. Yeah, we had it over here. So grab, and then you can see that everything is under the Kinect namespace that I mentioned earlier. So this is our topic of interest for today, _def_point. So let me select that topic over here and see that everything is being published. Okay, so I'm going to zoom in and you can see that the def points that are coming from the Kinect sensor are almost as if they were painted on the robot arm. Yes, if you have something like this, that means your alignment is correct and then you're ready to go. If you have anything rotated or any distortion or the plane is looking somewhere, then please you can go back a couple of minutes and then look at what I was talking about with the frames. It is very important. If you don't do this, if your planning is even going to be erratic. So let me just include a cube over here and then see that it gets reflected inside of RVS. So you can see that right here. Yeah, so our sensor is working correctly. Okay, so with that done, let's go and then make configurations inside of MoveIt, inside of the MoveIt configuration file that we generated the second day. Yeah, I think that was the second day. Yeah, I'm sure. Okay, so I'm going to, should I close this simulation? Do I have to? No, I don't really have to close it. So what I'm going to do is I'm going to remove the cube over here. I'm going to leave the simulation running, but I'm going to close RVS. So first things first, we're going to create the configuration file for the Kinect sensor. So we're done with the robot description. We don't need that package anymore. What we're going to do is first, but remember, first things first, what we have to do is enable the actuator joints for the robot and then get the, what do we call it, the joint trajectory server action server up and running. Remember, you have to do this to get the executions, the planning and then execution from MoveIt to be done correctly. So to do that, first then we're going to source. Let me do that inside here. We will open another shell for this. So I'm going to source the simulation workspace, hit enter, and then first then let's enable the joints, the actuator joints. So rush run inter_interface, and then you use enable robot.py, and then you give it the argument -e to enable the actuator joints. We're also going to do the same thing from the same package, but this time we're going to bring up the action server, which is the joint_trajectory action server.py. Hit enter to get it running. I'm going to hide this terminal over here because I don't need it anymore. So now that we're done with that, this is the package I was using from last week's session, which is the soya_moveit_config_2. I have to because I created it a second time, so you don't necessarily need, just the package name should match, that's all. So inside the config folder here, I'm going to create a new file. I'll be calling it the Kinect_config.yaml. Hit enter, and then hit enter again to open the file. I'm going to copy the configuration files inside here, then we'll go through it line by line. Okay, so we have the configuration files inside here, but to go through, let's go and then take a look at the MoveIt documentation that is being provided concerning that. There are actually two main plugins as of now, as of this video, that MoveIt uses for perception, for 3D perception. We have the type that uses a point cloud, and then another that uses depth image. But for today's session, we are going to be using the point cloud plugin. So first thing you're doing inside the configuration is what? We're selecting the type of plugin that we want to use, which is the point cloud Octo Map Updater, and then we also choose the topic on which the depth points are being published. That's what we're doing, and then here we just set in the range. We also do a point_subsample, then we're setting that one. What does this mean? We're saying it says choose one. Let's say we set it to 10, then we're saying that if we're given 30 samples, then we're just choosing 3 out of it if it's set to 10. And if it's set to, let's say, 5, then what we're doing is giving 15 samples, we're choosing 3 the same time. So this is kind of, how do I put it, there's a word for this, there is a word. We are sampling the depth points. That's what we're doing over here, but in this case we're setting it to 1, so 1 out of 1. That means we're using everything, we're not cutting down anything. But then you can do that in order to deal with overheads in your configuration or anything, that depending on what you're working on. Then we have the padding offset and then the padding scales, which affects the projected camera window from the Kinect sensor, from the sensor that you are using. Then we also have the filtered_cloud_topic, which is the topic on which the filtered cloud points have been published. What we mean by this is the robot does self-filtering. It removes any part of the robot that you're using from what is being published by your point cloud topic over here. So when that filtering is done, the point cloud topic without the robot part showing, without the robot showing in it, is usually being published here. So you basically can use this for debugging purposes and not, yes, just in case you're having problems with your robot. Okay, so we have our configuration ready to go. The next thing you do is, in fact, let me keep this open, we're going to be needing it. The next thing you do is to go to the launch folder inside the package that we generated, in this case the soya_moveit_config, and then we're going inside the soya_moveit_sensor_manager.launch.xml. You see that this file here is currently empty, there's nothing in it. What you do here is load the configuration that we just created. using the ROS param tag. So what we're going to do is ROS param, and then the command that we're using today is load. And then what are we loading? We're going to search for the file, which in this case, as we've been doing, we'll find the package, and then we just locate the specific configuration that we want from it. So Sawyer, but let me make this bigger, sorry. Sawyer underscore move it. Hey, what are you doing? Underscore config underscore 2, that's the name for my package. And then I'm going inside the config folder. Then inside the config folder, I want to load up the Kinect underscore, what did I call it, underscore config, yeah, dot YAML. Okay, then you close the tag. That is all we're going to do inside here. You notice you're just loading in the configuration file that we created. With that done, you can close it or leave it open. Okay, I noticed I misspelled the Kinect underscore, I misspelled it, Kinect underscore config. So I'm going to rename it right now in order to avoid any errors. So rename. And enter. Okay, so far so good. The next thing that we're going to be modifying is the sensor underscore manager. Okay, so this one we have some files already, some parameters already populated and then set up for us. You notice here that we're including the MoveIt underscore sensor manager, which is this file here that we just modified. Here we're including it, and then we're also setting the max range and then the resolution for the Octo map that will be created inside of MoveIt to represent any obstacles in the workspace. Okay, but then there is one more parameter that we need to be aware of, which is the Octo Map Frame. So you uncomment this, and then here it says the value should be some frame in which the robot moves. And as we've established earlier, we know that this frame is what is called base. In most robots you see base length, or sometimes the world or the Odom frame, but then in this case is the base frame. But then one thing also is this frame, if you're using a mobile robot, this frame is usually a static one, so probably the world, not the Odom, because the Odom keeps changing. Alright, so I'm going to be setting this to the base. Okay, so far so good, everything looks okay. Let's bring up the MoveIt interface and then let's see if everything works as they're supposed to. So I'm going to launch the demo.launch that we've been using. You see, today I didn't touch the demo.launch file. Everything was left the way we left it last week. So I'm going to do here ROS launch and then Sawyer underscore MoveIt config underscore 2 in my case, but in your case it could be just Sawyer underscore MoveIt underscore config. And then I'm going to launch the demo.launch file. Okay, so in order to visualize this, you need to use the graphical tools window. If you're using the ROS development studio, you realize that you can find the graphical tools window here right in the tools drop down. Okay, so RVS has been loaded, but then it's quite, the offset is wrong and we need to bring it into the center of the screen. To do that, you use the Windows Manager control over here, and then and you only have to do this if you are using the ROS development studio. Your local machine, I think everything will be different. Yes, 50 enter. Okay, so I'm going to double click to make this full screen, and I'm going to hide that panel over there because we don't necessarily need it. Okay, so we can see here that the Kinect sensor is working. You remember when we did the visualization earlier inside of RVS without the motion planning and everything, we saw the whole spectrum of the depth points that we're using. We have the same thing here again. So let me just go ahead and then include the cube here. You see that immediately it gets reflected inside of the planning, how do I put it, the motion planning interface, or the visualization inside of RVS. Yes, so you can, in fact, yeah, so let's do some planning over here. I'm going to do a random something, so update, yes, plan, and says waiting. Okay, let's see, no execution attempted. Okay, it couldn't plan that. Let's do the update again and then plan. Okay, so planning was successful. Let's execute that and then see. You see that the arm avoids the cube. So what can we see here? We see that the motion planning is taking into consideration the dynamic obstacles inside of the environment. That is the target for today's session. You see that you don't necessarily have to include collision objects or loading your work cell over here in order to do a pre-planning for MoveIt for your robot. You can use this, the 3D perception, and then anytime your environment changes in the spectrum of the Kinect sensor, MoveIt is going to take it into consideration. So here we can look at some of the planning that we're using from last session. For example, we had the planning the number 3, which is I think the Cartesian path. No, this is actually the Cartesian path, which is mainly recommended for when the end effector is approaching its final goal. Yes, and then we have that of the number 2, which I think is the joint states rather. Okay, our planning failed, it couldn't do that. Let me try 1 and then let's see. Okay, hold on. Oh, it worked. Good. So we're done. That's it for today's session, and I hope you learned something through this 5-week ROS camp with MoveIt. If you want to learn more about MoveIt, about planning, doing pick and place, and you can already tell the applications for this. You can do pick and place, and you wouldn't necessarily have to know the objects that you want to pick ahead of time. You can pick up the pose from relative to the camera frame, pass that to the end effector, and then direct the end effector to pick it up. Yeah, that's a topic for another session that we can look at. But then that's it for today's session. We're using 3D perception to affect the planning inside of MoveIt. Thank you for attending today's session, and then I hope you subscribe and then like our channel, and then you can visit the Robot Ignite Academy. I keep mentioning it. I mean, we have awesome courses over there. You can go there and then register with us. Yes, the ROS Development Studio enables you to program ROS irrespective of the operating system that you're using. You see, currently I'm using a MacBook, but then I don't need ROS installed on my system. Everything is web-based. If you're doing deep learning, and then we have these new computers for computing and all that stuff. You know, having your personal workstation is quite different. It might not be as powerful as you wanted to do learning and then all that stuff for your robot. But then here's the case: you have a web-based, very powerful server for you that you can use. If you are using the ROS Development Studio, you just go ahead and then you have like a 16 gig machine with about 3 or 7 CPUs running for you. Man, you already know the advantages for using this, and then I really recommend that you do. And then, you know, post in any questions that you may have regarding this and any other sessions, or any other question you may have regarding ROS, and then in due time we'll take care of it and then maybe do a class or a tutorial on it for you. So thank you, and then see you next time. Bye.